At a trench floor, clear water touches dark sediment under pressure capable of reshaping ordinary chemical behavior. Nothing visibly boils or burns, yet invisible reactions divide oxygenated water from reducing mud only millimeters below. The mystery is how carbon, nitrogen, sulfur, metals, and dissolved gases cycle inside this compressed, food-limited environment. Trenches receive material from vast overlying waters, then focus it into narrow basins where chemistry can intensify. A pale layer may mark recent deposition, while black patches can indicate sulfide formed after oxygen disappears. If you descended with a sensor, pressure would rise continuously while temperature settled near the deep ocean's cold range. Pressure changes gas solubility, molecular volume, mineral equilibria, and the energy available from some microbial reactions. Cold slows many processes, but it also preserves organic matter and increases the solubility of several gases. The result is not one exotic fluid, but overlapping chemical zones governed by supply, consumption, and transport. Seawater above the mud often remains oxygenated because deep circulation carries dissolved oxygen from high-latitude formation regions. Within sediment, microbes consume that oxygen while degrading organic particles delivered from the sunlit ocean. Oxygen becomes scarce. Other electron acceptors support metabolism in an ordered but locally variable sequence. The opening boundary is therefore dynamic, shifting upward or downward as fresh food, sediment, and water arrive. Understanding it requires following molecules through depth, rather than treating the trench as a chemically uniform container. The investigation begins with verified gradients, then tests why Hadal topography makes some reactions unusually concentrated. Organic matter reaches trenches as marine snow, fecal pellets, carcass fragments, and sediment carried downslope. Steep walls funnel some of this material toward the axis, especially during earthquakes and turbidity currents. Fresh deposits can contain more degradable carbon than nearby abyssal plains, although patterns differ among trenches. Microbes first use oxygen because it commonly yields high energy from organic matter oxidation. As oxygen declines, nitrate can accept electrons, producing nitrogen compounds and sometimes nitrogen gas through microbial pathways. Deeper still, manganese and iron oxides may be reduced, releasing dissolved metal ions into pore water. Sulfate reduction can generate hydrogen sulfide where sufficient organic fuel exists below the oxygenated layer. Methane may form in strongly reducing sediment, but its presence and concentration require direct measurement at each site. Other microbes can consume methane before it escapes, coupling carbon transformations to sulfate or alternative oxidants. These reactions are mainstream interpretations supported by pore-water profiles and microbial studies across marine sediments. At Hadal depth, their rates depend on organic supply, sediment age, mineral content, temperature, and pressure. Pressure can favor reactions whose products occupy less volume. Yet living systems respond through complex physiology. Microbial membranes must remain functional, and enzymes must retain structures vulnerable to compression. Compatible solutes and altered membrane lipids can help pressure-adapted organisms maintain cellular processes. Trimethylamine, N-oxide, is associated with protein stabilization in many deep marine animals, though cellular strategies vary. Microbes also use diverse adaptations, and no single molecule explains life throughout every trench. Sediment cores preserve vertical chemistry only if recovery minimizes mixing and pressure-related disturbance. Microsensors can resolve oxygen across fine layers, revealing boundaries blurred by coarser sampling. Landers measure near-bottom water and collect material without requiring a tethered vehicle at full depth. Laboratory chemical analysis identifies dissolved ions, gases, organic compounds, and isotopic patterns after careful preservation. Each method captures limited space and time, so agreement among gradients matters more than one striking value. The verified context is a sediment reactor powered mainly by material falling or sliding from above. The strange part emerges when trench geometry changes delivery faster than microbes and currents can process it. A turbidity current can bury oxygenated surface mud beneath a thick pulse of fresh organic sediment. Buried microbes then consume trapped oxygen, pushing reducing conditions toward depths that were previously oxidized. Later, oxygen diffusing from bottom water begins rebuilding the upper oxidized zone from the surface downward. This sequence creates chemical layers that record disturbance, recovery, and the quality of deposited organic matter. An iron-rich band may reflect redox movement, but mineral sources and post-depositional migration complicate interpretation. Black sediment suggests metal sulfides, yet color alone cannot quantify sulfide production or identify a reaction rate. High ammonium can indicate organic nitrogen breakdown, while transport and adsorption influence its final profile. If you examine a single core, its elegant gradients may represent one quiet pocket beside a recently disturbed slope. Comparative cores across walls and axes are needed to separate topographic focusing from local accident. Pressure also complicates recovered samples because decompression can release dissolved gases and alter living cells. Shipboard measurements may therefore differ from true in situ conditions, even when handling is careful. Incubations under simulated pressure can test microbial activity, but containers simplify natural gradients and community interactions. Researchers compare treatments cautiously, distinguishing demonstrated pressure responses from assumptions about field-wide rates. Another hypothesis proposes that trenches act as enhanced carbon burial zones because they collect organic-rich sediment. Some observations support locally elevated deposition and microbial activity at trench axes. However, earthquakes can remobilize buried material, and oxidation may return carbon to dissolved inorganic forms. Burial efficiency, therefore, depends on how rapidly sediment accumulates compared with decomposition and later disturbance. Trenches may preserve carbon in some sectors while vigorously recycling it in others. Hydrothermal influence offers a separate chemical possibility near tectonically active margins. Hot fluids can carry metals, sulfide, hydrogen, and altered seawater, but vents are not established at every trench bottom. Volcanic arcs usually lie beside trenches rather than directly along their deepest axes. Without temperature anomalies, mineral deposits, or fluid chemistry, hydrothermal explanation remains speculation. Serpentinization can produce hydrogen where seawater reacts with exposed mantle rock. Yet geological access must be demonstrated. Likewise, unusual methane does not automatically imply deep geological seepage because microbial production may occur within sediment. The strongest interpretations use several compounds and their spatial relationships instead of one ambiguous chemical signal. What remains unknown is the full balance among reaction, burial, lateral transport, and exchange with bottom water. This chemistry sustains life because microbes convert otherwise inaccessible compounds into biomass and metabolic products. Deposit feeders ingest sediment, digest microbial and organic material, then return altered particles through fecal deposits. Burrowing animals move oxygenated water downward, expanding reaction surfaces and changing iron, sulfur, and nitrogen cycling. A scavenging amphipod detects a dissolved food plume, swims toward carrion, feeds, and releases waste compounds into surrounding sediment. That behavior converts a brief carcass arrival into localized chemical enrichment and microbial growth. Bacteria respond to fresh substrates by increasing activity, consuming oxidants, and steepening nearby concentration gradients. When the pulse fades, diffusion and bottom water exchange gradually restore more oxidized conditions. These Q-action consequence sequences connect visible animals with transformations occurring at molecular scales. Chemistry also controls preservation, determining whether shells dissolve and whether organic tissues persist after burial. Deep seawater is often undersaturated with respect to calcium carbonate, encouraging dissolution of carbonate remains. Local pore-water reactions can either intensify dissolution or raise alkalinity enough to alter mineral stability. For you, the mud may look inert, but each centimeter can contain opposing reactions separated by thin boundaries. Those reactions influence how much carbon remains buried and how much returns to ocean circulation. No single trench dominates global biogeochemistry, yet combined Hadal systems reveal processes missing from smoother seafloor models. They also preserve evidence of pollution, including metals and synthetic particles transported with natural sediment. Contaminants can adsorb to mineral or organic surfaces, then move again when redox conditions dissolve carrier phases. This creates potential exposure pathways, although toxicity under Hadal conditions remains poorly quantified. Human stakes include climate accounting, pollution transport, and understanding ecosystems before disturbance expands into deeper waters. The responsible conclusion links trench chemistry to global cycles without inflating its measured planetary contribution. Future evidence must record chemistry directly at pressure across undisturbed sediment-water boundaries. Long-duration landers could follow oxygen, temperature, and turbidity before and after natural deposition events. Closely spaced cores would map how reaction zones change from steep walls to the central axis. Pressure-retaining samplers could reduce gas loss and physiological shock during recovery to the surface. Analyses of carbon, nitrogen, sulfur, iron, and manganese together would constrain competing metabolic pathways. Stable isotope patterns could support process identification, but they require models that acknowledge transport and mixed sources. Repeated observations after earthquakes would test whether mass flows reset gradients and accelerate temporary carbon processing. Seasonal measurements could connect surface productivity pulses with delayed chemical changes thousands of meters below. Microbial activity experiments should reproduce pressure, temperature, and realistic substrate concentrations as closely as practical. Genetic potential alone cannot establish an active reaction, so molecular findings must be paired with chemical rates. Likewise, a favorable reaction calculation does not prove that organisms perform it in the natural trench. You should expect different trenches to yield different balances because geology and food supply vary widely. The decisive advance will be a time-resolved budget showing what enters, reacts, remains buried, and escapes. Until then, strange profiles are evidence of active transformation, not permission to invent unknown chemistry. Return to the clear water above dark mud, where oxygen penetrates only as far as supply outruns consumption. Every deeper layer records another negotiation among pressure, minerals, microbes, and material delivered from the distant surface. At the bottom of deep-sea trenches, the real chemical mystery is measurable change across boundaries we have barely watched through time.